Okay, today we're going to talk about Kirchhoff's laws. Notice the very odd spelling of Kirchhoff. Gustav Kirchhoff, Kirchhoff, is the way that name comes into English. And for lab next Tuesday, we'll be doing the Kirchhoff's law.
Is that the one? No, that's Ohm's law.
Yeah. So I will simply disregard the Ohm's law pre-lab quiz because, some people, I'm sure, I haven't looked, but I'm sure some people did do. They're like, well, we don't have lab today, so there's no point in doing the lab. So I will just disregard that one, put it into not for credit category on Moodle. Make sure you do the Kirchhoff's laws pre-lab quiz before lab. Andrew is going to work as our TA for at least this lab and hopefully the rest of the semester. So, be easy on the young man. He's your classmate. And he will be spending time with me so he knows what he's doing in lab. Okay, I think that's enough for the announcements. Ryan, what in the world?
I just locked my hands together.
It's a magic trick.
Watch me get out.
Okay. Interesting. Okay, last class period I talked about Georg Ohm and his law. Georg Ohm knows that most materials had a fixed relationship between the energy drop per unit charge across them, which we call the voltage, and the rate at which charge is going through, which we call the current. And so we call this the resistance that applies to these types of materials. And the resistance has to do with actual resistance to charge moving in the material. And so the resistance of an object has to do with the stuff it's made of. And you can think about it, you probably have heard of the water analogy. You can think of the resistance in a resistor like you would the resistance to current flowing through a pipe. If you have a pipe that has a smaller area, smaller diameter, it's going to be harder to push water through. It's going to have more resistance to pushing the current through. Now, if you just have a trickle, it's not a big resistance. Or, it's not a lot of energy lost. But if you have a big amount of water going through, you're going to have a lot of energy lost because of the resistance to flow. If it's a longer pipe, it's also going to have more resistance to flow. And so it's the exact same thing for electricity. The resistance of an object is equal to this rho, like that's the Greek R, is the resistivity of the material. So this is specific to the material. Also, sadly, the resistivity is generally a strong function of temperature. So you change the temperature and the resistance changes. So for instance, if you take a regular tungsten filament light bulb and you measure the resistance of it, it's very different when you measure that resistance than when you actually turn it on. Because when you turn it on, it gets much hotter. Because it got much hotter, its resistance changes accordingly. Then it's proportional to the length of the resistor. The longer it is, the bigger the resistance. Inversely proportional to the cross-sectional area. So if you have a cylinder like this, the cross-sectional area is the area of a slice when you cut across the cylinder. And of course, if it was a different shape, you have to use a different method to determine the area. But that area is the cross-sectional area, not like the surface area or something like that. So if you cut across it perpendicular to the direction current's flowing, the area you get is that area. And this is the symbol for resistor, as I said in class last period. So that's a little background just to know that resistance depends on the material as well as the dimensions of the material and the temperature of the material. And I didn't include the linearized form of resistivity with temperature here. Whoops, this way. Now, not everything is going to obey Ohm's law. An example is a superconductor. Superconductors are materials that have virtually no resistance. So this graph here is showing a resistance as a function of temperature graph for a superconductor. And what you see up there is at very low temperatures, the resistance is really, really low. But then when you get up to a temperature that we call the critical temperature, all of a sudden that resistance jumps way up. And so this here is actually, says Hg, so that must be mercury, right? I didn't even know mercury was a superconductor. It does say that, yeah. Resistance of a sample of mercury is 0 at very low temperatures. It's a superconductor up to 4.2 Kelvin. So that's the TC, the critical temperature. You can see you have to have a really cold temperature to make that a superconductor. By the way, mercury is going to be a solid at that temperature, just in case anyone's thinking about, oh, it's liquid. Not that temperature, it's not. We have other superconductors, things like the ceramic, yttrium, aluminum, barium, I think it's copper, oxide. I think that's what they make them out of, which have higher critical temperatures. And you guys may have heard of room temperature superconductors, a search for room temperature superconductors. What they consider a high temperature superconductor now is anything that's superconducting at a temperature above the temperature of liquid nitrogen. So yeah, normally we don't think of liquid nitrogen as super warm. But for superconductors, they consider that high temperature because liquid nitrogen is plentiful. When I was working at a DOE lab, we just made our own. Because at a DOE lab, you know what they have lots of? Money. And so this was at Battelle Pacific Northwest Laboratory. It's now Pacific Northwest National Laboratory. They just collect nitrogen from the air because the air is 79% nitrogen. And then they, I think they compress it and make it into liquid nitrogen. So, got that covered. Sign conventions. This is actually important. This is not trivial. Our conventions, I wrote these in class on Wednesday, but when we have current going through a resistor, I always start, every time I work a circuit, I will start by drawing the direction of the current. And you might say, what if I don't know the direction of the current? That's a fair question. The answer is, I pretend I know. If I'm wrong, in the end, I'll get a minus sign for my current, and that'll tell me, oh, I guessed the wrong direction. So there's no risk in assigning the wrong direction for the current when you start the problem, because in the end, if you get a negative value for the current, you just know I assigned it in the wrong direction. Yeah.
Wait, so then how do you know whether your answer is supposed to be negative or positive, or is it just supposed to be
well, if you have to have what's the current in the direction of the arrow, or what's the current to the right, or something specified to know what sign to put with it. Okay. If they don't, you're just going to put a magnitude. Okay. Right, because direction is an important aspect. So I indicate the direction of the current. Now here's something funny and technical. Technically, current doesn't have a direction. It flows that way, but it's not a vector. The reason is because current density is a vector and the way we calculate current. But for us, we draw the direction of the current. And then we assign voltage drop. Ohm's law says you have a voltage drop when charge goes through the current. So you're always going to have the positive side and the negative side. The side with the tip of the current arrow is the negative side. The side with the butt end of the arrow is the positive side. So once you draw that arrow, it's going to tell you which side to mark as positive and which side to mark as negative. Now, when we talk about Ohm's law saying change in voltage is equal to current times resistance. That change in voltage is the positive minus the negative here. It's the voltage difference from one side of the resistor to the other side. It's not, sometimes you say the voltage in the circuit is this. Technically, that's always incorrect. It should always be the voltage in the circuit at this location with respect to this location is this. Right? The voltage isn't 10 volts here. If this is considered 0, then it's 10 volts here. Because voltages are always voltage differences. One of the reasons I said the textbook is just wrong in trying to make its difference in potential, electric potential and voltage. It's always a difference. So in this picture over here, notice the arrow is going the opposite direction. What does that tell you about the voltage? Which terminal is positive, A or B? B, right. I mean, it seems like a trivial thing, but it's really important for solving our problems. Now, when we look at these, I drew pictures of these in class on Wednesday. What is this technically a picture of? A cell, right. And always the long side is positive, the short side is negative. And the natural current flow for a cell should be that current comes out of positive. Because remember, current is the rate of, we don't say it, but it's implied, positive charge flow. Even though in reality it's electrons, negative charge moving through the circuit. When we calculate the circuit, we talk about rate of charge flow, which implies rate of positive charge. And so we talk about it as if there's positive charge flowing out of the positive side. And so the current is coming out of the positive, going into the negative. Yes?
Again, in one of our reading quizzes, it showed like a picture of that. And it says, what is it? And it's the answer battery. So
wrong!
That's why I was like,
But it didn't give you the option of cell and battery, right?
I don't think so.
Yeah.
I would
Because then you have to fight, right? If it says battery for that, you're like, not really, but yeah, I understand why you pretend. So just, to finish up what she said, the real symbol for battery, what would that look like? Yeah, like that. That's a battery because it's more than one cell. And I always have to explain to students, yeah, I said battery. It's because back when I was in high school, Eddie Murphy came out with a comedy album, Delirious. And in this album, there is a segment on rich people's cars talking. Yeah. A friend opened the door and said, ding, your lights are on. And it goes, oh yeah. In the hood, we have our own talking cars. And the day I came to my car, opened the door and said, ding, your lights are on. Ding, what is you, deaf and blind? Shh, turn your blinking lights on. And the car door and said, say, man, someone stole your battery. I say we go get the bad person. That's why I say battery. Okay? All has to do with Eddie Murphy. As you can tell from the words that I removed, it's actually not appropriate content for you to listen to. But it's why I say battery sometimes. What was it?
So Google it.
No. The older I get, the more highly inappropriate I realize it was. Except for ice cream. I got some ice cream. You don't have any. Okay. Actually, that's not appropriate either, is it? Anybody know that? Yeah, it's making fun of poor people. It's not good. I'm sorry I ever brought that up. Difference in alternating current and direct current. AC/DC. It is the name of the band that they always play before raid or game, and thus it actually causes a visceral reaction to me when I hear Hell's Bells. But that is not the point here. AC stands for alternating current. DC stands for direct current. Direct current, your current is always traveling the same direction. Our picture here is idealized direct current, and that's what we're going to work with when we say DC. When we say direct current, we're going to mean not only always the current going the same direction, but it's also constant, not varying. So DC current's just going one direction. A battery always produces DC, always produces direct current. AC, that's what we have right here. We have an outlet that has 60 hertz, 120 volt AC power. What that means is that the current alternates in direction. So sometimes the current is going left, sometimes it's going right. If I stick my finger in here, sometimes current will go in my right finger and out my left finger. Sometimes it'll go in my left finger and out my right finger. And all times I'm putting my life at risk. Don't do stupid things. I don't know, I'm in a mood. Back when I was teaching at PUC, we had at Redwood Adventist Academy, a place that burned down last year in the fire. They had a science fair, and I came out there to represent PUC. And they had a pastor giving a worship service before we started. And so he did a science worship service. Talking about when he was a kid, he liked to take clothes hangers, metal clothes hangers, and unravel them and stick them in the outlets. And I'm like, you crazy, crazy man. First of all, that's dangerous, and now you're telling a bunch of kids, I know kids like from 5 up, They're going to go home, hey, Pastor said you can do this. It just shocks really bad. Don't do stupid things. At the end of the lecture, I'm going, of course, the rate I'm going, I'm not. I have a thing on electric safety. And there's a lot of ways to die with electricity, and we don't want you to experience any of those. So please, don't do. Just talking about AC for a moment, just so we have it in there. Alternating current, the current is going back and forth. On average, the charge isn't moving then. The charge is moving back and forth. So you might wonder, how do we get anything out of that? Well, we can still take energy out of that charge anytime it's moving because V equals IR. V is the voltage, the energy per charge. And so if I have current going this way, I'll have energy losses, the charge goes that way. If it's the other direction, I'll have energy losses goes that way. So you have an incandescent light bulb, piece of tungsten. That tungsten is going to get hot regardless of which direction the current's going through it. And so it's going to convert electrical energy into thermal energy getting hot. Gets hot enough that it gives off light in the visible range because it's taking away energy for each time the current travels either direction. Now, something else you might wonder. I said the voltage coming out here is 120 volts, 60 hertz. 60 hertz, we've already learned about frequencies. That's how many cycles it does in a second. It does 60 cycles in a second. But what about the 120 volts? It cannot be the average. If I have voltage that's going like this, what's the average going to be? 0. So the average voltage coming out of the wall is 0. Whether the circuit breaker is tripped or not, the average voltage is 0. So that's not a useful term. The average voltage just isn't useful for AC. So then we can talk about things like we can talk about the peak voltage. But what we actually calculate is the RMS voltage. And so for a sinusoid, you do the calculus, take the, what does RMS stand for? Remember from last semester? Root mean squared. So what you do is you square root the average of the square. So you do that calculation. It's not actually hard because that's just equal to the square root of integral from 0 to the period of the maximum sine of omega t dt over t. V is a constant, so it's the integral of sine squared. Oh, I forgot to square. Right, because the square that we had there. So you have to do the integral of sine squared. Integral of sine squared is 1, well, it's not hard. And so what this ends up giving you is equal to V naught times square root of 2 over 2. So the RMS voltage is the peak voltage times the square root of 2 over 2. Or peak voltage divided by the square root of 2 if you want to write it simpler. We like to have rational, not divided by square roots. So we write it this way. So if our voltage, if VRMS is equal to 120 volts, then I can solve for the peak voltage. And it's like 170. I'm putting numbers from memory. It's 169 point something. And so the peak voltage coming out of the wall is actually going between plus 170 volts and minus 170 volts. We call it 120 volts because that's the RMS calculation. Did you actually do it?
Yeah, it's 168.
168?
Yeah.
Did you actually do square root of 2?
No, I didn't.
Yeah, it's not 1.4, it's 1.40,
Okay.
some other digits. I was like, no, it's not 168, it's 169 something.
169.7.
Yeah, 169.7, that sounds right. Other things that are unimportant for today, the voltage is not always 120 volts. Sometimes it's 110 volts. That's why sometimes you hear 120 volts, sometimes you hear 110 volts. They adjust the voltage depending on demand. When there's a little demand, they'll let it go up to the high end. When there's more demand, they'll bring it down. And when there's really a lot of demand, you have a brownout where they bring it down too much.
Why do they call it brownout?
Because your lights are, instead of bright white, they start getting dimmer.
That's kill your computer sometimes.
Yes, it will. Question?
Just a curiosity thing. Why is it 220 in Europe? Is there a reason why it's double?
Yes, it is exactly double. It's 110 times 2 is 220. It's 220 to 240 is their range.
Yeah.
And what they're using is, let's see. Yeah, I think it's still single phase. It's just twice the voltage, which means for the same power, you have half the current. It's a little more dangerous of a voltage.
I was just curious if there's a reason why there's this double compared to ours if you know the does it really matter?
Well, we've kind of coordinated, but not exactly. You also have places that use 50 hertz instead of 60 hertz. So like if you look at a lot of your things, they will say 110/220, 50 to 60 hertz. They actually make them so they'll run anywhere, which is good. When I was in college, we went on a choir tour to England, and they did not use a transformer and plug their blow dryer in and melted it.
Yeah.
It was funny. Okay. Was that?
But you need the special adapters. I didn't know you could melt something.
Yeah.
I mean, it makes sense.
Yeah, I mean, it's basically the blow dryer just has a wire in there that you put current through. And so you double the voltage, you're going to double the current according to Ohm's law. It's going to get hotter. Double the voltage, double the current, and the power is 4 times higher. Okay, so this is a typical circuit showing how electricity works. You have the battery, it pushes out positive charge away from the positive side, attracts positive charge to the negative side. That's all a big lie, right? Because it's actually the positive side is attracting negative charge, the negative side is repelling negative charge. But we talk about it as a positive charge. So the current flows out of the positive side, goes through the resistor, and returns. Current is not lost in a circuit. All of the current that goes out of the battery comes back into the other side of the battery, or in this case, it shows the battery and then the circuit shows the cell. You see my confusion. Yeah.
So I'm kind of jumping ahead a little bit. So like if we had a question like this on the test, if we had a question like which way did it flow on a test, which way is the correct answer? The correct answer is it would say what direction does current flow. Yeah.
If it says does current flow, then it's clear. It goes out of positive into negative.
Okay. Even though that's not how it actually happens.
It's how current actually flows. It's not how particles actually flow.
So current from the positive to the negative?
Yes. Now here is a picture illustrating the two differences. You have a wire and you put an electric field difference on the wire. Or not electric field difference, an electric field. And that electric field puts a force on the charge. And so the charge moves in response to that force by the electric field. Who thinks about electric field when you talk about wires? Nobody. But this is what's really going on. The wires are acting as a wave guide. They're guiding an electromagnetic wave that's traveling down the wire. And that electromagnetic wave is carrying electric fields, and those electric fields are then going to cause charge to move. And so for the same electric field, notice in both pictures, the electric field is pointing to the right. If it was a negative charge carrier, the force from the charge carrier is opposite the electric field to the left. If it was a positive charge carrier, it would be to the right. The net result is the same current. A negative charge to the left is the same as a positive charge to the right. And so in some semiconductors, picture A is actually what happens. So this is what happens in some semiconductors. And then the question is, what's moving? And the answer is its whole migration, which is a whole different whole topic. This is how it works in electric wires. I didn't think the charger was on right. I was clearly right. So in our electric wires made out of metal, it's electrons moving. How fast do you think electrons move in a wire? Super fast. On the order of maybe 1 centimeter per second. That's super slow, isn't it? The electrons, their drift velocity, how fast electrons on average move, is on the order of centimeters per second. Now, the electrons themselves are moving fast, but the electrons are basically bouncing around, carrying off of everything. So the electrons are just bouncing all over like this. And on average, when you put a electric field on the wire, they will start drifting, so they're slowly moving over. And so that drift speed is very slow. But then you have the question that you thought you were answering. How fast does an electric signal travel? That's very fast. That's because the electric signal is the electromagnetic wave that's traveling outside of your conductor. The conductor is a wave guiding that electromagnetic wave. And so it travels at the speed of light in the material. So if you have a wire with no insulation, the signal travels at the speed of light. If you put insulation on it, it slows it down a little bit. So when I turn on the light switch, the reaction is pretty much instant because the signal is traveling at the speed of light. But the electrons are going to take a very long time to the light switch. That is individual electrons. Okay. Last topic before we do something useful. Are internal. Remember from last class period, at the very end of class, I talked about the lead-acid battery and talked about you have a chemical reaction. As soon as you use it, the chemical reaction has to start up and your voltage will drop a little bit because the chemical reaction is now operating, trying to regain equilibrium. So your voltage always drops from a battery when you use it. And so we model that by saying that a battery is, or a cell, is two things in series. So this is the real battery or real cell. You have an internal resistance, which is a small resistance in series. Remember, we defined in series last class period, with an ideal voltage source. So now when I put that notice, I have an E there. That's the best I could get on the computer. I need to try again. But it's the best I could get on the computer for that symbol. That symbol is supposed to stand for electromotive force, which is the term we use. It's not correct, but it's the term we use for the terminal voltage of the battery when it's not in use. So if you were to take a voltage tester and check the voltage across the terminals of the battery while it's just sitting out there, not connected to a circuit, that gives you the EMF. And so that's the voltage you have if you're not using it. As soon as you use it, your terminal voltage is going to drop. So the actual terminal voltage in use is the voltage difference between those 2 points. And so voltage terminal is equal to, according to Ohm's law, the EMF is the voltage from here to here. And then what direction should current be flowing in the circuit? I know it has a current drawn, but just to make sure, what direction should current be? Through this resistor? Through the internal resistance. What direction? Up. Up because it should be going into negative. And so with that, I can say, well, that means the positive side is the butt side of the arrow, and the negative side is the head side. And so this, if I go from this point to this point, that's a voltage drop. Going from plus to minus is going down. And then going from here to here is a rise because the long end is always positive. So the terminal voltage is the EMF minus the current times the internal resistance. So the terminal voltage is going to drop as I use the battery. Now, if I want to calculate what the current is in this circuit, I have two resistors. How are those resistors connected? It's in series. How do you know it's series? Well, it's not parallel, but you can have things that are neither series nor parallel. So the way to tell for sure is any current that goes through this one has no option but to go through that one. If current going through one has no option but to go through the next one, then they're in series. And so how do we add resistors in series? You just add them. Series is easy. And so now I could replace that circuit with a simpler form. Okay, so I change it to a battery. So there's my EMF, and there's R total equals R load plus R. Current, again, should come out of positive and go to negative. And now I can say, well, look, the voltage difference across this is the EMF, because that's the difference in the top and bottom is the EMF. So using Ohm's law, that's how I calculate the current going through the circuit. And once I've calculated the current going through the circuit, now I can go ahead and calculate what the terminal voltage is, or the voltage across that load is, by using Ohm's law. You knocked her phone down? So that is your simplest circuit problem ever. You know, you're going to see that? Yes, once. Then you go on to harder things. So here's a harder thing. How do I analyze this bad boy? Notice I have the voltage. I have my R1, that's R internal. That's the internal resistance. And then I have R2 and R3. How can I find the current everywhere in the circuit and the voltage differences across each resistor? We have a method. Leslie?
Isn't that one like two-step type of thing? And you can do the parallel first, and then it'll turn into one, and then you could do the series?
That's exactly what you do. You look and you say, do I have anything that's in series? Do I have anything that's in parallel? Do I have any resistors that are in series with each other?
Wouldn't you do the parallel one first?
I have to, because the answer to the question is no. I have no resistors in series. Any current that goes through here can split. It has two options. It's only in series if there's only one option. It's got to go from one to the next. So I don't have anything in series, but these are in parallel because the tops are connected together. And there goes my battery.